Welcome back, everyone, to CSE 291D 234 Data Systems for Machine Learning. My name is Arun Kumar. Continuing our industry invited guest lecture series, it's my pleasure to have Joshua Patterson from Nvidia here today. Joshua has a very exciting career that has spanned the White House, census work, and now at Nvidia, he's heading the engineering effort for Rapids, which is a new software framework from Nvidia for accelerating data science workloads end to end. And I've heard a lot about Rapids in the last couple of years and spectacular successes in some competitions and so on. So I was really curious to learn more and get our students exposure to Rapids. So thank you, Joshua, for making the time to come visit us. Protocol for the talk, would you prefer questions during or towards the end?
Anytime. I want to be as interactive as possible.
Wonderful. Okay. So students, feel free to raise your hand. I'm happy to look at that, or also post it on the chat, and then you can also unmute yourself and ask the question. With that, I will give it over to Joshua. Take it away.
Awesome. So I'm going to turn off video while I present because I find seeing myself distracting. So I'm the Senior Director of Engineering for Rapids. I'm glad Keith and Brad could join the call. I think John Z and maybe Mark are going to join later. So I'm going to give you a quick overview of what Rapids is, why we built it, the current libraries, some of the current integrations. Then I'm going to pause, take questions, and then we can kind of just pivot from there based on people's interests. And so there's a lot of slides. They're all on docs.rapids.ai/overview. Latest. We'll always give you the latest version, but you can also see our kind of overview deck for the last 4 or 5 releases. And so, GPUs are kind of the core of Rapids. Rapids is fully built on CUDA, and GPUs just have, just really amazing, just pure performance. So the compute performance for NVIDIA GPUs is kind of unparalleled. And what's really catching up to that is bandwidth. We can get data to the GPUs faster. On the GPUs themselves, they have really fast memory bandwidth. Typically, the memory speed is about an order of magnitude faster than system memory. The communication between GPUs is significantly faster than going across CPU socket to socket across machines. And then with all the advances in InfiniBand, we're really kind of pushing the best node-to-node communication in a technology stack. And so there have been a lot of Spark talks. We've been following the Spark community since basically 2017. Matei and all of his talks talk about networking as 10x. Well, it's actually closer to networks like 100x, really in the last 5 years. And storage speed has gotten tremendously faster with, things like DDN and Weka and Bass and a bunch of other hardware players. But compute hasn't changed. Well, CPU compute hasn't changed, but GPU compute has gotten significantly faster. And so when you kind of leapfrog the compute side, it actually shifts the balances to where networking and storage have typically been the bottlenecks. And we're going to talk about how Rapids addresses both of those things to really allow data science to happen on the GPU. And so, our goal is really end-to-end acceleration from ETL, ML, graph analytics, full integration with deep learning frameworks, as well as visualization libraries. We really want to do everything on the GPU as much as possible. So let me see if I can, there we go. And so, a few of us have kind of been working on this since, the beginning of the big data days. And so if you remember anything about, Hadoop, I'm not sure that, this is kind of as relevant, people's school now, but it was a lot of reading and writing to disk. And that was really what made it, slow. Spark came along and just really kind of revolutionized big data because it kept everything in memory primarily. And you got these massive speedups over like things like, MapReduce and how and other core, MapReduce frameworks. But there was still more to be desired. And so traditional GPU compute gave another improvement over that, but it was really hard to program. You had to write things in CUDA, and you were constantly doing things on the CPU compute intensive things on the GPU, and you were moving data back and forth, and you had to manage your own memory, and it was simply just a pain. And so one of the things that we really wanted to do was to improve the bottlenecks of GPU computing. And so that the biggest bottleneck was just moving data. Data movement really hurts performance. And so if we had two things running on the GPU, like essentially like an ETL engine, and then we wanted to visualize the data or do machine learning, we basically have to make a round trip between system memory. So we'd have to take data on the GPU, move it off the GPU, convert it to a new format, and move it back onto the GPU. And so our goal is to get rid of that, that copy and convert. And surprisingly, it was pretty easy, because at the same time around 2015, 2016, Apache Arrow was just starting to like get its legs. And it was trying to do the same thing, but on the CPU side. So removing all copy and converts, as well as being language agnostic. And so we thought this was great. A language agnostic, standard way to represent data in a columnar fashion was really kind of the foundation for vectorized computing. And what we realized is not only was it language agnostic, it was hardware agnostic. So this format was great for the GPU as well. And so now with Rapids, we can do the same thing kind of that sparked it to the big data ecosystem. We're basically getting a 50 to 100x improvement in speed, and we're keeping data in the GPU as much as possible. And so yes, this means you need a large amount of GPUs and a lot of GPU memory, but luckily that's the way that the industry is trending as well. And so, in kind of a real world use case, we were benchmarking, Rapids to kind of industry standard benchmarks, and rewriting the code purely in Python, we see a significant improvement, typically about 7x normalized for cost. Recently, this has improved to about 17x. We have a blog, and actually I will just jump to that really fast. Our blog, medium.com/rapids-AI, we talk about many different things, and there's probably over 100 blogs now, and they're all really great, typically between 4 to 7 minutes. But most recently, we took that 5x improvement that we had initially in the slides. We're here at this 872nd point, and that's about a 7x improvement TCO. Now with significantly less hardware, so only 6 servers, we can do 10 terabyte workloads even faster and cheaper. So we're about at like a 17x, and what would take CPU systems 3 or 4 hours, we can do in about 11 minutes. And so I want to go back, and I'm going to talk about this for a second. So first off, before we know anything about the libraries, I want to talk about these end-to-end benchmarks. And I know it seems backwards, but I really want to get rid of the kind of the conception of, is it fast? Is it scalable? Is it complete? I don't think any open source library is ever complete. We're always going to be adding more things to it. But I think it's complete enough to do very large scale benchmarks, win Kaggle competitions, and be used in production by companies like Walmart and Capital One, to save hundreds of millions of dollars every year. So, it's production ready, but it's not complete. And why we like to show benchmarks is, 10 terabytes is basically the 95th to 98th percentile of data sizes. Most people don't work with more than 10 terabytes of data at any given time. And so this benchmark reads data from disk, it does some type of ETL, whether it's structured, semi-structured, or unstructured, and then it does some type of machine learning, and then it writes the results back out to disk. And so doing all of these 30 queries 20 to 30 times faster than a CPU system is great, but doing it for 17 times cheaper, I think that's the more important thing that we really appreciate about Rapids. Not only is it fast, it's fast and cheaper. Typically, speed comes with a cost. And so Francois Chollet basically had a really great talk at AnacondaCon 2 years ago, and I really miss in-person conferences. And so he's the creator of Keras, if you're not familiar with him. And he's saying, like, the difference between a data scientist and a Kaggle grandmaster is really just their iteration time. Category masters are really good at doing these iteration loops. They're really good at the technology stacks. They're really good at just like optimizing their time very well so they can experiment, see the results, get new ideas, experiment results, ideas faster than other people can. And that's really a fundamental driver of Rapids. We want people to be able to do data science, how they do data science, just faster. So learn nothing new. Don't think about, how are you using your GPUs? Are they utilized? Really kind of forget all of that and just do data science, but just do it faster. And so I'm going to skip over like the specifics of 0.16, but one of the things that Rapids does is kind of connect to this whole data science ecosystem. It's less of a single library as a bridge to other libraries. The goal of Rapids is really a collection of kernels that accelerate things in the Python ecosystem, and hopefully in the future more so in the Java ecosystem as well. It's meant to accelerate things like pandas and scikit-learn and Dask. And even if these libraries don't want to have native integration, we mimic them so closely it almost feels like you're still using those libraries. And so Rapids at its core is just doing that. So you basically take your PyData ecosystem, pandas, scikit-learn, NetworkX, the deep learning frameworks that all run on the CPUs, and then we're just going to GPU accelerate them and make them API compatible. And so cuDF looks like pandas, cuML looks like scikit-learn, cuGraph looks like NetworkX. We add new functionality, we add more scalability, we obviously make them faster. And so now you can do the same thing that you were doing beforehand, just 50 to 100 times faster, which typically results in 10 to 15 times cheaper. And so why Dask? A lot of people ask us, why not Spark? And we actually have a podcast coming out next week or the end of this week where Keith and I talk about our early beginnings. And essentially, this slide sums it up. Dask is deployable everywhere, whether it's in HPC with Slurm, PVS, LSF, or on the cloud with Kubernetes, or on Hadoop clusters with Yarn. It's extremely easy to scale. You can use it on a laptop. You can use it on a supercomputer. We run Dask on Selene. We run Dask on Oak Ridge National Labs supercomputer called Summit. Dask is used over on 10,000 nodes for NCAR, for weather stuff through the Xarray and Pangeo project. Dask has 2 million downloads a month. So it's a very popular Python native scalable framework, but it also at its core, it's very modular. And so the things that we didn't like about Dask, like how communicating over TCP sockets is really slow, we could just replace those things. And so we could just replace that with like OpenUCX. So we replace the CPU compute libraries with our GPU compute libraries and Rapids. And we could basically just start plugging in these faster things and everything would just get faster. And so this is why we really, enjoyed using Dask. When we first came to Nvidia, we're like, we're going to accelerate Spark. And then we realized that was really hard. We have an amazing team. We have 3 maintainers of Spark at Nvidia now, working on accelerating Spark. We have a large team working on it. But we realized we could just move a lot faster with Dask. And the Python ecosystem is just a lot more complete for GPU acceleration. And case in point, integrating OpenUCX was pretty trivial. We built Conda packages. We had a pretty amazing team working on it for a couple of months, about 6 months. And now we just get this pretty major speed up going from just normal TCP to things like InfiniBand and NVLink. And so essentially, we scale up with these PyData libraries, these typical single core, single threaded Python libraries. We scale them up to the GPU and make them multi-core and parallelized within a GPU. And then we scale those out with Dask and OpenUCX. So everyone with me so far? Awesome.
Any questions from the students? No, let's continue, Joshua.
So cuDF is our data frame library. This is where I believe most people spend their time, data munging. When I started my career at Freddie and then eventually Fannie and a bunch of other places in financial services, I spent most of my time cleaning data. That was the slowest part and the most painful part. And a lot of times it's a lot of coffee drinking and feature engineering and very little model training. And so when we launched Rapids, we kind of, Jensen, our CEO, said, draw out a day in the life of a data scientist. And this is kind of like our, rendering of what we imagined data science life like, and he just loved it. So he put it on screen with all the typos and everything, and it kind of just stuck. So the ETL stack, if you will, of how we build a library. And so this is kind of my my pitch of Rapids. Early on we talk about users and their benefits, and it's fast and scalable and great. From the rest of the talk on, I'm going to kind of bob and weave like a sign pattern between developers and end users. So this is more so talking about developers and how we're building library, and then the end user benefits of this approach. We would love people to join on both sides, using it and also contributing it. Currently, Rapids is about a third of its contributions come from outside of Nvidia. Within Nvidia, that other 2/3, only about 2/3 of that is actually the core Rapids team. The other third is just other people at Nvidia being really excited about the project and just contributing to it on their free time. And so while Rapids is shattering these benchmarks and doing all these really great things and helping companies save hundreds of millions of dollars and all these even being used in COVID research, it still can only do as much as developers can expand the code base. So now in 2021, our big goal is to add more developers at the core of Rapids, because we know that the users are growing. That's kind of taking off on its own. What we really want to do is kind of motivate, recruit, grow our developer base. And so all of our libraries start with CUDA. And then we use CUDA libraries on top of it, like Thrust and Cub and Jitify and libcu. And there's a bunch of like CUDA library primitives that we use that make it a lot easier to write things like CUDF C++ layer, which is called libcudf. And so then we take libcudf, and this is where we have things like our join functions, our group bys, our string library, and all this is in libcudf. And then we take Python and we bind Python to that. And so in libcudf, as I said, it's our CUDA C++ library. This is where all of our optimized code is for basically doing things, data science things on the GPU as cleanly and as efficiently as possible. And then we bind that to Python. And so the end user can do things like cudf.read_CSV, and you can read a CSV. There's a lot of other things that we do that make this really powerful. Numba is a just-in-time, a JIT compilation library that works on the CPU and GPU. And so, as people want to write new arbitrary functions for data science, we allow people to write that in Numba and then apply that to their data frame in a vectorized manner. And so, a very natural extension of Rapids is basically saying, hey, we want people to just write Python and it always targets the GPU, whether it's explicitly through CUDA or it's doing some type of JIT compilation through something like Numba and going directly to PTX. And it's really fast. If you just go on Twitter and look up CUDF and pandas, you'll see a bunch of people talking about how much faster CUDF is than pandas. If you go on Kaggle and search for CUDF, you'll see the same thing. It's significantly faster, and it's just it has all the core functionality people need, like merges and joins and group bys and whatnot. I'm gonna pause for one quick second. I need to help my wife with something. I'll be right back.
Any questions so far?
Bradley, this is Arun. So I have a question.
Yeah.
So far, so good. One question about this particular graph. This is on synthetic data. What data set is this?
This is on synthetic data.
Got it. Okay. And this is on CPU, Intel CPU with how many cores?
Technically, I think it's like a 20-core CPU, but it's pandas, so it won't effectively utilize all 20 cores of that regardless. And then generally, things like merge just get bottlenecked by your memory bandwidth before actually utilizing even a full single core of compute.
I see. Okay. So does that mean this is a single threaded CPU execution?
Yes, but again, like for Panda specifically, running, for example, a merge, if you use, for example, Dask or Spark to take advantage of all 20 cores, it will actually go slower, and that you just get bottlenecked by the random memory access bandwidth you have available to you, and then just adding the overheads of having different threads having to communicate and synchronize actually just adds more overhead than using just a single thread does.
Got it. And that's an issue with the pandas join operation, the merge.
Yep. I mean, it's just the nature of join algorithms in general are not embarrassingly parallel, where you need like a partitioning strategy in order to effectively utilize things.
Got it. Okay. Yeah, I mean, in the database world, they've studied parallel hash joins that can give you not exactly linear, but I don't think pandas or any of these Python library tools actually implement that yet.
That's actually exactly how Dask does kind of multi-threaded or multi-node joins, where it basically does a hash partitioning first, but then you need to do an all-to-all to exchange those partitions before doing local joins. And that all-to-all communication is really expensive.
I see. So are you going to talk about how you tackled that on the GPU?
Yeah, we will actually, Josh, we'll get to that in a little bit.
Okay, sounds good. That's right.
Yeah, and so one of the things is, a lot of times we're like, oh yeah, this has been done in the database world. There's also one of the reasons why we do benchmarking. A lot of database vendors are even now realizing they're like, holy crap, we didn't realize these things would be so fast on the GPU. It's just always, I'm talking about this in our podcast, kind of reasoning versus first principles. On first principles, GPUs just have faster, random memory access bandwidth. And that's just a first principles fact. It's just, I have a bunch of data and then I want to, join something on a key and I want to have a hash partition. It's just faster if I can have all that in GPU memory. And so when you're writing these algorithms to exploit these things, even against, very well optimized, CPU implementations, and Keith, I'm blanking right now. Nikolai talked at a conference recently about this. We had a really great talk.
The conference that he talked at?
Yeah, he keynoted.
I want to say it was VLDB.
Yeah,
VLDB. Yeah, thank you. And so he keynoted it, and it really just shows that, like, GPUs, especially with NVLink and NVSwitch, which, is essentially think whatever InfiniBand bandwidth is, almost another order of magnitude of performance of bandwidth between GPUs within a node, a single server. And when you exploit these things, you just have better performance, even better than state-of-the-art CPU implementations. And so a lot of the things that we do with Rapids is really just exploiting memory bandwidth access on the GPU, and doing things efficiently, and then just exposing that through a Pythonic interface. So starting from the most optimized thing that we could do on the GPU, and then just binding it to other languages.
Got it. Oh, looks like Joshua's back.
Yeah, sorry. Can you? That was me talking. I don't know if.
Oh, sorry. Go ahead. Sorry, Joshua. Let's resume
where
you left off.
So that was me actually the whole time. So I was actually done with that slide.
Sounds good. Sorry.
Yeah. Oh, no worries. And for completeness, in Rapids, we need a string library. You can't really do data science without a string library. It's something that wasn't common, didn't exist on the GPU. And so, we built a full string library. It's something that people didn't really think would be performant or fast. And what we're realizing is it's great. It does really well. You can do normal string things, split bind, upper lower, extract, cat typecasting. We have a tokenizer. We have a bunch of kind of just core NLP functionality, and then we're going to just continue to optimize it and add more and more JIT compilation of strings in the future. We have full readers and writers, and so essentially each one of our reader over kind of state-of-the-art dual socket implementations, we're seeing about an order of magnitude speed up. And so that's true for our CSV reader, Parquet, Orc, JSON, Avro, And this is always one GPU compared to 2 sockets. Most systems that we recommend are always 8 GPU systems. And so with this, we're talking about reading in raw data directly from disk. The faster the disk, the better, directly into GPU memory. And then from there, we do things like decompression as well as decoding. And so we go from literally compressed, Parquet files, we decompress them, we de-encode them, and then we convert them into Arrow. And so by the fact that we're doing all this on the GPU, and again, memory bandwidth is really fast, we're typically seeing like a 10 to 15x improvement. And that's on top of like dual 20 sockets compared to a single GPU. And so with 8 of them, sometimes we can read data 50 times faster. So a problem that's even kind of very trivial, where you're reading a bunch of data, scanning it, deleting a few rows, and then writing it back to disk, that whole workload is faster just because every step of that workflow is faster on the GPU, even if the compute itself is trivial. And then we can do this for other things as well. So it's not just ETL. Because we have interoperability with all the deep learning frameworks and array frameworks through the CUDA array interface or DLPack, we can basically expose all the NumPy things in Python. And so we primarily depend on CuPy and Numba for this. CuPy is a drop-in replacement for NumPy, and they actually are really serious about their compatibility with NumPy and have like in their docs, like what's compatible and what's not. And again, we see this kind of the same thing for element-wise functions, for FFTs, for array slicing. We're seeing these 100x improvements, even for more complex things like SVDs and matrix multiplication. And then we can scale this with Dask and Dask array, similar to what we can do on the CPU side, and where you see like a single GPU all the way up to multi-node, multi-GPU. On the machine learning side, we have QML. Again, same pattern. It starts with CUDA. We build on top of it. One of the things that we do here, though, is we go from CUDA libraries to a thing called QML prims. And these prims are things that we see that are very common across machine learning algorithms. So we decompose machine learning algorithms into families, and with those families, they have similar kernels. So we write the kernels once, and then we wrap those in C++, so then other kernels can use them, and they're basically calling these groups of kernels, and then we bind all that to Python. And the main reason for that is it might be slow to develop the first kernel, but we're making it very modular and easy for people to pick up the building blocks. One of our most read blogs of all time is our TSNE blog. It's had like 20,000 reads on Medium. It was written by an intern, and it's about 500 times faster than the scikit-learn implementation of TSNE. In fact, it's so fast that it's like one of the more popular things that people do in Kaggle. And it was an intern who wrote our TSNE implementation just using the QML prims. Undergrad, hasn't even graduated yet at the time. And so we really take this approach where by making things modular, it makes it easier for people to contribute to Rapids. And it also makes it easier for people to use Rapids. And so here's the difference between QML and QDF versus pandas and scikit-learn. We have a bunch of algorithms. I'll talk more about them later. But generally speaking, here are their speedups versus scikit-learn. Some of the decomposition algorithms are hundreds of times faster. Some of our worst case scenarios like k-means, which is only about 15 times faster, 10 to 15 times faster. And these are on 1, 2, and 4 million data sets on the left, synthetic data sets, and then 16, 32, and 64 on the right. When you get to real world data sets like Bosch, Airline, Higgs, Epsilon, which are very common in the GBDT world, we're seeing about a 20 to 30x improvement on inference with our Forest inferencing library. And comparing a single GPU to dual sockets for things like XGBoost, we're typically seeing anywhere between 3 to 20x improvement. The smaller improvements are typically on very small data sets. So when you have like a 40 and 80 gigabyte GPU and the data set's only a gigabyte, it's just really hard to kind of effectively utilize all the CUDA cores on the GPU, whereas the Airline data set's a 12 gigabyte data set, And so as the data gets bigger, our improvements start to grow. And typically what we see is things that typically take multi-node CPU implementations, we can typically fit them on a single server because we just have a lot of GPU memory and is more dense. And we get much bigger speed ups when the data set grows, like in the hundreds of gigabytes, whereas that's something where Spark MLFlow would have to distribute that across nodes. We also have within Rapids like full integration with all the different cloud frameworks, whether it's SageMaker, Azure ML, Google AI Pipeline, but more importantly, a bunch of open source tools as well. So like Ray for Tune for hyperparameter optimization, Optuna, Teapot, and then also Dask ML and MLFlow for model management. And so typically, if you want to do HPO on something like the airline data set using random forest, it's about 20 times faster and about 7 times cheaper. And then we also GPU accelerated CHAP. Again, same thing. Somewhere between about a 10 to 100x improvement on performance comparing a single GPU to dual socket. And this is one thing that people have always said that's been like really kind of painful is the explainability side of tree models, and it's just really slow to use CHAP. So we wrote a GPU implementation. Again, it follows the CHAP API one for one. You just download the GPU version of it along with CHAP, and you just kind of just follows the same API essentially.
Joshua, I have a question. This is our
Go for it.
So can you talk a little bit more about how this is parallelized? So what are these prims? What are these operators? Are you parallelizing the histogram computations for the trees? Are you parallelizing, like placing different trees on different PUs? How exactly does it work under the hood in the GPU?
So there's actually there's a paper about this from, not this one. I will look up the most recent one from Rory, where it really goes in depth on what we're doing. This is a good one. This is the older one. We have an updated one that talks more about some of the recent improvements. But yeah, so we're actually, this is the difference between what XGBoost does and LightGBM. So LightGBM, it actually uses the CPU for the histogram for the binning, and then it just uses the GPUs for the gradient reductions. For XGBoost, we actually do everything on the GPU. So it actually moves all the data to the GPU and does both the histogram calculation as well as the solver side, all in the GPU, and then as well as inferencing. So the data actually never leaves the GPU. That's actually basically the trick for all of Rapids. We push everything to the GPU. And so earlier we were talking about with joins, we do the hashing on the GPU. We have a few different hashing methods that we have for the GPU. And then we probe on the GPU as well. And so data never leaves the GPU. All the functions have been implemented as efficiently as possible in CUDA or some type of CUDA like primitive library. And so a lot of these things just live in Thrust itself. So like the sorting algorithms that we just use the sort that's in Thrust. So we always build on top of state-of-the-art CUDA libraries, and then we just add more and more abstractions as we go up the stack.
Got it. So then if all the data is sitting on the GPU, is it required that the data set fit entirely in GPU memory, or do you shard the data and go to DRAM appropriately when there's a call needed?
For ETL, we do that. So for most things on a data frame, we can shuffle data out the GPU, and we're working on methods to overlap compute and data movement more effectively. But that's actually not too bad. So we can even spill to disk with our ETL library. For our machine learning library, though, and for graph analytics, all the data has to fit fully in the GPU. So if you have a 1 gigabyte data set, that's easy. If you have a terabyte data set, you typically would need 2 systems. So with our latest GPU systems can have 640 gigabytes of GPU memory in one system. So with two systems, you can basically fit a terabyte. And that's why we can do 10 terabyte workloads in 6 systems, mainly because the ETL can spill to system memory.
Got it. Okay, thanks. Let's continue.
And sorry, the other thing is, I normally end with this, but I might as well just jump to this really fast. So on our GitHub, you can also go to any library. And so for QML, we can go into like CPP, and we have the source of each one of our algorithms. And so the whole library is open source, and so we don't actually hide really any of how we're developing any of this. And so we have many different libraries. So Raft is one of our Prim's libraries. So Raft is used between both cuGraph and QML. And inside of Raft, you basically just have all these different primitive functions. And so if cuGraph needs some type of distance matrix calculation that QML is using, they both can just add Raft in their build process. And so we basically try to pull as many things down as we can to make it easier for people to develop across both libraries. And so here's where we are today, and here's where we'll be by the end of the year, hopefully. Obviously, some things are, they might slip, given the holidays and other things. But we have, pretty much most of the core libraries, multi-node, multi-GPU. A lot of the time series libraries, there's just no need to make them multi-node, multi-GPU because you just don't have data sets that large. You typically do many different time series models, but not one time series model that's that large. And similarly with things like TS&E. cuGraph is similar. Q at the bottom. Where this one gets a little bit interesting is we have multiple different primitives layers. So we have dynamic graph primitives in cuHornet. We have static graph primitives in Prims and Gunrock and Raft. And then we build algorithms across these different primitives. And then we use Python to bind those to Python. Really, because graph can be expressed in many different ways, where there's a dynamic graph or a static graph. There's a frontier-based approach, and there's a kind of a laws-based approach. And so the graph ecosystem is a little bit more opinionated about how you implement algorithms. And some implementations are just better than others for certain higher-level algorithms. And so we want to make sure that we have the freedom and the flexibility to basically use the best approach for the algorithm that an end user needs. We have a lot of graph algorithms. I'll go to a slide at the end about that. But here's one of those kind of times where, NetworkX, a package that gets a few million downloads a month, we're 1,000 times faster because NetworkX is a pure Python library, and it's getting compared to a very well vectorized and high GPU utilization cuGraph. And so one of the things that we did is we want to make it easier for NetworkX users to use cuGraph. And so essentially, cuGraph can accept NetworkX graphs and subgraphs, and even with the penalty of moving data to the GPU and then moving it back to the CPU. For small graphs, there's almost no improvement. But even when you get above 400 nodes, which is a really, really tiny graph, you start seeing 2x, 5x improvement. And a 50,000 node graph is still relatively small. You're seeing about a 300x improvement. And so that's kind of comparing us like your standard Python, social network analytics package. Then you compare it to something like Spark, where you can take 100 8-core nodes, so 800 cores total, and compare that to 16 GPUs, which is 800 cores in the cloud will cost you more than 16 GPUs in the cloud will cost you, and you're essentially getting like a 90, you get a significant speed up. It's like a 200x improvement, and this is all because our cuGraph multi-GPU implementations of these algorithms are just really great. in 0.17, we're going to have more multi-GPU implementations, as well as multi-node, multi-GPU. And we actually have, and Brad, correct me if I'm wrong, we deprecated our multi-GPU cuGraph, and it's now just either single GPU or multi-node, multi-GPU.
Correct. Yeah. Well, multi-node does the same thing as, single node does. So multi-node, multi-GPU is what we're going for.
Awesome. So I'm going to pause there. So those are our three main core libraries. We all scale these with Dask. They're all kind of built on top of each other. cuDF is kind of at the bottom. cuML and cuGraph both depend on cuDF, as well as Raft. And then we just kind of have this like growing sets of libraries above that. I'm also going to do a quick time check.
Oh, we have some time. So the lecture slot goes on till 2:20, but we want to keep some 10-15 minutes at the end for the questions. So like if we can wrap up in like 10-15 minutes, that would be great.
Perfect. So after that, we just basically have other libraries. So cuSpatial is a combination of cuDF and Thrust, and is meant for geospatial. Again, a healthy amount of functionality, and all these slides are here, so I'm going to go a little bit quicker now. But the speed up over some of the state-of-the-art geospatial libraries is very large, everywhere from 300 to like a few thousand X improvement. And so we've had a lot of our early users of cuSpatial really just completely change how they're doing geospatial analytics. Rewriting whole we have one startup who they've been doing geospatial analytics on Spark for over 3 years now. They rewrote their whole code base in Rapids, and they said what used to take them around 14 to 16 hours, they can do in less than 15 minutes. And really what they're more excited about is their cloud bill is significantly cheaper. We did the same thing with signal processing, except cuSignal, instead of having a Python layer, it primarily just uses CuPy and Numba. These are all the benchmarks with V100. With our latest generation, essentially we just double the performance. And again, if you're doing signal processing, it's it's basically a drop-in replacement for SciPy signal. And one of the things back to interoperability, signal processing deep learning is really kind of growing in popularity, especially with 5G and other things, and the signal intelligence. And so being able to just go directly from this pre-processing in cuSignal that's very Pythonic directly into PyTorch is really useful for people who are trying to do deep learning in the signal community. We did the same thing with Clix. So Clix is our cybersecurity library. It's built on top of all the things that we just mentioned in Rapids. And the whole point of it is really just kind of this like one-to-one integration with different cybersecurity products. So we have a lot of different packages, network mapping, asset classification. And so the goal of this is we had a lot of people on our team who came from cybersecurity backgrounds. Myself, many others came from kind of the three-letter agencies or working for DARPA or other government-sponsored cybersecurity initiatives. And we just realized how much people were spending on cybersecurity. We just had to do something better. And it really kind of brings together all the different graph, machine learning, anomaly detection, very high speed data streaming. And so Clix is kind of a natural evolution of real world problems that we faced in the past that were just too expensive to solve. One that we particularly like is cyber. So I think most people are probably familiar with BERT models. And they're typically used for some type of NLP and sentence completion or question and answering. We realized that BERT was also really useful at parsing unstructured logs. So we could write we basically could train a network to read in an unstructured log, and then we would train it on what that parsed log would look like. And with a few terabytes of data, or a few tens of terabytes of data, we could actually train these models that were really accurate at reading Windows event logs, raw data, and parsing it correctly, even for malformed logs or logs that were basically never seen before. And they're much more flexible and frankly faster than like regex. And so, this is like something that's really kind of has like real world, applications of deep learning for something that, I don't think it's kind of the most commonly thought of things. It's just like log parsing. And then we can feed it directly into cuDF to do, analytics like group bys and joins, as well as graph analytics. And so it really starts to make the whole data science pipeline a lot easier. One of the core things that makes our Cyber so fast is our subword tokenizer. And so our tokenizer is very fast and faster than the Python version of the Hugging Face tokenizer. But they also have a Rust-based kind of experimental tokenizer that's extremely fast. And the GPUs, as you can see, at batch size of 1,000 is about 4 times faster than dual socket, and that just kind of continues to grow and plateau off around 16, 17x for very large batch sizes. And then also with clicks, we wanted to kind of do some more higher level system engineering. So we found a way to integrate this directly into Splunk. We use Splunk internally, and so Splunk has a way where you can extend their SIM, basically where you can write SQL and it just targets a new backend. In this case, it's BlazingSQL and clicks. And we've done something very similar, which is data visualization in general. We built a cross-filtering library called CoolXFilter. We integrated with Plotly, very common, popular Python data viz library, as well as data shader, bokeh, HoloViews, etc. And really what it does, it allows users to load hundreds of gigabytes of data into memory and get sub 100 millisecond responses for these cross filtering and interactive data vizzes, where it would just be fundamentally impossible to do that without waiting tens or even hundreds of seconds with some of the CPU implementations of these libraries. I think this is really important for not only cybersecurity, but just kind of interactive data exploration in general. So I'm going to pause there. I hope I'm really quiet. Are there any questions?
Questions from the students? I don't see any on the chat so far, but probably we can continue, Joshua, and then we can take questions at the end.
Sure. And so finally, we have a lot of people using Rapids, contributing Rapids, adopting Rapids. We work with a lot of different open source projects. The 3 that we like to point out are NVTabular, BlazingSQL, and Streamz. NVTabular is a part of Merlin. So Nvidia, we have a team that just does recommenders. They started building a recommender platform, and they realized that they need to accelerate the data loading part. And then they just basically just use Dask, cuDF, and Rapids. And so they realized how great it was, how easy it was. And so NVTabular is essentially a Python wrapper on top of Dask, cuDF, specifically for recommenders. BlazingSQL is a full SQL engine built on top of Rapids. This is how we get some of the really great results at 10 terabytes is using their SQL engine. It uses Apache Calcite. So again, things that were already used in the big data community is using Apache Calcite to parse SQL queries, and then it uses libcuDF to execute the kernels, and it basically sits on top of Dask as well, so it can then pass the data back to Dask cuDF, Dask QML, Dask cuGraph, etc. And so BlazingSQL, even if you only have a single GPU, it has really great out-of-core execution and overlapping of memory. So it does really, really efficiently at really large workloads, even on a single V100. And then Streamz. Here's an example of a project where we didn't really want to focus on streaming. We just wanted to focus on batch analytics and building machine learning and inference pipelines. But we had a team internally who was spending millions of dollars a year on streaming. And they're like, with fast networking, it should be possible. So they took the Streamz library, which is basically a Dask and Python library for stream processing, and plugged in cuDF and created Streamz to basically make that easier for deployment, as well as fixing any holes or gaps that that were in these libraries from a compatibility standpoint, as well as they created an accelerated Kafka reader. So Kafka is just a standard messaging queue and essentially we can bypass some of the Python layers and directly we have a library called librd-kafka that pulls directly from the C++ layer of Kafka into the GPU. And so we're getting about 4x TCO improvement. With streaming, we can't talk about how it's quote unquote faster because we can't go any faster than the stream. So this is purely one of those things where we can make it cheaper. And so that's really exciting. And again, NVTabular, BlazingSQL, Streamz, these are all libraries that the core Rapids team doesn't have a part in. And these are just people building on top of it to build other types of systems. And we really hope that there's more of this in the future. And those are just 3 examples. There's a lot of genomics projects integrating Rapids, drug discovery, and there's actually a really great talk where Oak Ridge National Labs is using BlazingSQL and Rapids for COVID drug simulation analysis, and they were basically like on 300 or more GPUs, they were getting sub-second response times on some of their analytic queries. That if they use all the CPUs in Summit, which is 27,000 nodes, they don't think they would get that level of performance. And so it just really shows like kind of this bridge between HPC and data science is happening in the real world with Rapids today. And so HPC users who are doing this really kind of high level of engineering drug simulation can still just write SQL queries to analyze their data that's being generated by the same cluster. And it just works. And it utilizes the GPUs very efficiently, and it's fast and it's easy. And it's the same thing that our enterprise customers are using as well. So please contribute back. We would love people contributing to the libraries, filing bugs, using it. We have Rapids notices for any type of changes that are going on in Rapids. It's pretty easy to get started. Google Colab, app.blazingsql.com gives you a free T4. We have a bunch of blogs, like even this presentation is all online. We have this kind of interactive GUI for selecting the right version and getting the conda install command. Our docs are extremely clean, and we spend a lot of time making sure they're user-friendly. And as I said, we have a lot of blogs. We have over 100 blogs now. We blog about 6 to 7 times a month. Everything from here's how to do this, ML pre-processing, here's a Kaggle notebook that won a contest and here's what they did. Here's how somebody's deploying Rapids in production. Here's the new features in the release. And so, we're going to continue to expand Rapids. And so we typically just think that very short, digestible blogs are the easiest way for people to look for what they need to get started. And so, GitHub, Conda, NGC, NVIDIA GPU Cloud for container registry, or Docker Hub are all places where you can get Rapids. Any cloud, any deployment, whether that's Yarn, Kubernetes, Slurm, what have you. Rapids is, we have documentation for all these things. In fact, there's Rapids.ai cloud. And so it basically breaks down how to deploy Rapids on any cloud environment, whether it's single GPU or multi-node, multi-GPU. So that's it. I would really love for you to join in. You can follow Rapids on Twitter, Dask, Arrow, and a bunch of our other projects that we work with. You can follow me on Twitter, talk a lot about Rapids. But ultimately, we really just want to grow the ecosystem. It's fast, it's cheap, it's exciting.
Great. Thank you, Joshua. Thank you for the nice talk. Let's see if we can get the audience to applaud, so we do this virtually. Thank you for the talk. I think we have some time for questions. Questions from the students, the audience. Feel free to unmute yourself and ask.
Hi, Joshua, can you hear me?
Yes.
Yes, I can.
Yeah, thank you so much for the talk. It was great. So as you saw that Rapids has like a bunch of components. So I wanted to ask, how far along are you in the implementation of some of these? For example, take QDF. So can I do everything with cuDF that I can do with pandas right now?
I think Pandas has 900 or so APIs, and I think cuDF has like 350, 400. But again, I think it's enough to do any benchmark, and we have really large commercial users using it. And then my favorite compliment of all about cuDF was one of our Kaggle grandmasters who now works at Nvidia. He said around 0.14, he competed in 3 contests, and he didn't have to do any workarounds in cuDF. It just worked like it should in Pandas. And I think that's kind of the mark of sophistication that we want to get to. I don't think we'll ever have parity, but if a Kaggle grandmaster can use it and not have to do a workaround, I think that's enough functionality for most of us mere mortals.
Yeah,
Yeah,
sure.
just to add to what Josh said, the API footprint for Pandas is actually over 5,000 APIs, believe it or not. It's insane. And part of the problem is even Pandas maintainers don't really know exactly what is or isn't expected Pandas behavior in a lot of situations, where we're at the point now in cuDF that basically all of our unit tests, we compare against Pandas to make sure that we are basically following behaviors as expected, where every time Pandas even does like a patch release, for example, our CI routinely finds issues that kind of upstream Pandas CI does not find. And so we are very much working with the Pandas community to try to be as compatible as possible, but there is a ton of situations that just Pandas is so flexible of a library. There's just so many situations where it gets used in ways that kind of the Pandas maintainers and developers don't really think about or know about or account for. And it's hard to make the statement that we're 100% compatible, where I'm pretty sure Pandas maintainers would agree that they aren't 100% compatible with Pandas behaviors. So it's a really hard statement to make. But all differences from kind of Pandas APIs and Pandas behavior, we effectively treat as bugs in cuDF, where if you go to use it and you see something that isn't implemented or doesn't work as expected, please just raise GitHub issues for us to look into.
And again, I think that's one thing where we try to be as interactive with other communities as possible. Keith meets with many Pandas developers and maintainers, and our goal is not to replace any library or say anything negative about any library. Our goal is to work with them because the closer we are to Pandas, the more things that we can do with Dask, and it just makes it easier for other upstream libraries to have interoperability with us. And so that's really important for the Rapids team.
Okay. More questions from the audience? Supam, go for it.
Hi, Joshua. Thank you very much for the interesting talk. I think it's a very important system. I have 2 questions. So the first question is regarding, so you that this Rapids library and in general GPU execution can give you high speedups, but also it's cost effective. I would like to know whether it's like across the board or like what decisions I have to make in order to pick whether I need to run this workload on CPU-based analytics system or a GPU-based analytics system. Or in other words, like going to the future, do you expect like both silos of analytics software coexisting, or like do you expect like GPU-based analytics to take over CPU-based analytics? The second question that I have is more of a technical problem. So most of the applications and algorithms that you showed you were previously thought to be very hard to be parallelized on GPUs. For example, like string tokenization and string processing and some of these other like ML applications, because they have like complex branching behavior, or like the memory accesses are not regular. Like that can cause like thread divergence and other like GPU kernel level bottlenecks. So what special techniques do you take in these libraries to overcome these issues? Or like or is it the case like even with these like limitations, GPU execution is still faster than like if you compare it for CPU execution?
So I'm going to start with the latter first, because I think it segues very much so into your first question. Even with some naive non-optimal implementations, especially like in our string library in libqdf, things that we didn't think were going to be that great, which, you know, we don't get super high GPU utilization just because of the memory bandwidth, and some of the CPU implementations also not being that great either. We still get some really great speed ups. And even when you're comparing kind of state of the art versus where we are, just the raw power of the GPU typically makes up for a lot of like, you know, engineering shortcomings, for lack of better words. That being said, we also have some amazing engineers and researchers at NVIDIA. And so really, really hard problems, we have teams of people who think about them in NVIDIA research, and then we have a team called DevTech, developer technologists, who work on optimizing CUDA for these problems. And so, you know, when you work for a company who wrote CUDA, any type of limitations of CUDA, we can actually just improve on within CUDA. So I think it makes it easier for some of these things to just start to naturally get better and faster over time. And so, so in a way, really, even with just naive implementations on top of like CUDA, using these primitive libraries like Thrust and libq and others, the implementations still turn out pretty good. And to your first question, in fact, they're so good. Typically, we see for most workloads, once you have over 4 gigabytes of data, there's really not a time where the CPUs aren't cheaper and faster. And a lot of people really kind of question that. And I think that's kind of where some of the excitement in the Kaggle community really is. You know, we see a lot of people being like, oh, well, you know, trying to find corner cases. And typically it's only when you're in like the megabytes of data. Really, once you even get into gigabytes of data, it's really that a GPU isn't faster. And, you know, that used to happen more so around 0.8 and 9. But those are typically bugs. Some function not being very well tested for certain types of sparsity or you know, data layouts. We improve those, and the library is just getting pretty hardened. So I think, you know, CPUs are great for smaller data, for very slow streams of data, and for very non-computationally intensive, like slow inferencing. So like if you're doing a logistic regression and you have a batch size of 1, you know, it's really going to be hard to utilize a GPU well for that type of inferencing. You know, but if you're doing, you know, batch sizes of 100,000, even something not computationally complex, like, you know, logistic regression inferencing, just because your batch size is so large, I can parallelize that very well across the GPU. And so, you know, so far, and this is kind of getting confirmed in Kaggle and a bunch of other places in real world work loads. Once you get over, you know, 4 gigabytes of data, you really just, you're in a sweet spot for GPUs.
Thank you.
Great. I have some questions too, but let's give the students some more chance to ask questions. Most questions from the students? No, okay, so I have a question, Joshua. So it's a very impressive set of libraries across different applications and different kinds of data analytics tasks. Can you say a little bit more about workflow that consists of multiple invocations of these? Like typically, like when you're doing a complex multimodal analytics task, like social media analytics, you have graph data, you have text data, you have relational data, and you do some graph algorithms, then you bring it back to Python memory, and then you do some post-processing, and then you issue a relational style query, then you run a machine learning algorithm. Would the data move back and forth, or do you think future, looking forward, Rapids will enable the entire Python workflow to exist on the GPU, including control that happens on the CPU today?
So they don't move back and forth today. In fact, you know, for whatever's implemented, we it all happens on the GPU. cuGraph, cuML, cuDF, all the, you know, derivative libraries, they all communicate on the GPU. We can pass data to PyTorch directly. We're not even copying and converting the data. We're literally just passing pointers through, like, you know, DLPAP or CUDA interface, CuPy, Numba. So with the data not moving, we're doing exactly what you're talking about. We can literally have a data frame, you know, subset that, get some graph features, merge those features back onto the data frame, do TS&E. In fact, one of the most recent Kaggle contests, you know, they use TS&E for tabular data to make images, and then they use CNNs to train those images. And they would have placed in gold, but they did some pre-processing because they just didn't trust the model. They just like, this is just too good. So they did some pre-processing to kind of normalize. And so they actually wrote a Kaggle blog about this, where if they did no pre-processing, just TSNE to CNN directly, training large batches, they would have placed in the top 10. And so a lot of times, because it's so fast, you can try these kind of like esoteric methods that are ensembling, graph analytics and ML and deep learning and get these really great results, but you're doing it so fast. A lot of times people are like, I think I'm wrong. And we're seeing that a lot with our Kaggle grandmasters. The speedups are scary. So they always just assume they're overfitting. But really they're just trying more complex things. They have to kind of rethink what overfitting looks like. One of them said that, we kind of revived SVM from the graveyard because,
right.
Our implementation is about 500 times faster. And in the neurotrends contest, everyone started off in deep learning, and they basically was a CAT scan or a CT scan. My wife's a doctor, and she'll be upset that I don't know the difference between these different types of scans. But it was some type of brain image scanning that I can't think of off the top of my head. And everyone was using deep learning. And then, somebody on the Kaggle team used SVM and jumped to number 3. And by the end contest, 30 of the top 40 implementations were all using SVM from Rapids because you could just iterate faster. And SVM is a lot easier to understand than, a deep learning model.
Okay, fascinating.
Yeah.
Following up on that, a lot of the work that you've done in Rapids with the kind of parallelization of these computations and using the multiple processing units available, the memory access behavior, they are exploiting the functionality of the GPU very well. But are the lessons portable to other environments? Do you think there are ideas in Rapids that can be applied to other environments, back to the multi-core CPU environment or embedded systems or kind of Internet of Things devices and stuff like that? What is your thoughts about that? Or is it very specific only to GPUs?
The bandwidth and the performance of specific GPUs. I think, no, not I think. I'm positive that Nvidia produces just really great hardware. And so one of the things that we always like to joke about is we're betting on the hardware. So the hardware is just really great. So it allows us to do things. But you're right. A lot of times it's just we have better implementations as well. And so, we work with a lot of different communities to improve their implementations. A lot of people are actually seeing what we're doing in Rapids and oh, that's a really good implementation. So it's improving things like Pandas and scikit-learn. And, a plug for our interns. This is also why we, love hiring a bunch of interns. There are a lot of different projects where someone's like, hey, here's this thing in this other GPU space or CPU space, or I want to standardize APIs, and they come to us with projects. I forgot the last student who asked the question around thread divergence, but we actually had 2 different interns studying strings and thread divergence and different methods to improve this, using different sorting algorithms before you run the string algorithms, and different ways of partitioning data within warps. And so we love to have people come in with fresh ideas to kind of challenge what we think we know about GPUs. And the diversity of thought is really what's useful. I mean, the Rapids team is fully geographically distributed. We have literally people in every continent, Australia, Asia, Africa, Europe, North and South America contributing to Rapids, except Antarctica.
Okay.
We don't have any, we have no contributors in Antarctica yet, but we welcome interns. So if you're looking for internship this summer, and what we really want to do is we've built a bunch of primitives. We've done a lot of things, and so we want to plug those into other places. My goal when I joined Nvidia was to make data science cheaper, not faster, but just cheaper. It was just too expensive to do cybersecurity. A healthy byproduct is faster, but we love to expand that ecosystem, make things cheaper.
The very closely related, how fast you can iterate and how cheap it is end to end. So one last couple of questions. Virtualization is becoming more common, even on GPUs, especially for things like serverless and resource disaggregation in modern cloud settings. How well will Rapid play with schedulers that allow multi-tenancy on GPUs?
Very well. So multi-tenancy is a tough thing. So I'm gonna talk about like what NVIDIA is doing with GPUs in general. So we have MIG on our A100s, multi-instance GPU. So I can take a A100, I can chop it up into smaller GPUs. Basically 7 GPUs is the limit. And I can treat each one of those like their own GPU. So Rapids works completely fine with MIG. We work on vGPUs as well. We work, so with the vGPU, our grid technology, you can take a GPU and you can, basically say, all right, these are multiple different GPUs. So MIG is at a hardware level, vGPU is at a virtualization level. And, we work, completely fine with vGPU, and it's tested and, run through our CI. So if you have like a big GPU that has 48 gigabytes of memory, and you virtualize it where each person has 24, that's completely fine. I do find it odd that when people are like, well, can I virtualize a GPU into multiple GPUs and then multi-GPU those GPUs? I'm like, well, maybe you just take that one GPU and just use it by itself. It might be better. And so typically there are some performance trade-offs. So if the user is trying to use multiple virtualized GPUs on the same GPU, I would say just use that GPU. But yeah, virtualization and hardware partitioning work fine.
Sounds great. So speaking
the other thing I would add, we do have actual users that they have kind of bottlenecks either before or after the GPU kind of processing portion. And what they'll actually do, the GPU driver has a mode that basically allows you to kind of schedule things concurrently on it, where they will run multiple processes targeting a single GPU and put the driver in that mode and basically just get full concurrent execution in doing that, where kind of the either kind of pre-GPU or post-GPU things, basically they can alleviate some of those bottlenecks by just kind of hammering the GPU with more work and then letting the driver kind of concurrently schedule that work as possible. So we totally see those things as well, and those work well with Rapids too.
Got it. Sounds good. Thank you. So last question, longer term trend, Nvidia has acquired ARM now, and they are interested in other sorts of deployment hardware. And in the inference landscape, there's like a whole cottage industry of startups and chips. Google, of course, came out with their own TPUs and whatnot. Where do you see this landscape going for the data science hardware ecosystem? Of course, for training and model building and stuff, GPUs are still the dominant. On the deployment side, where do you see the landscape going?
So there's, I don't know if you're familiar with NVDLA. I always have to double check that.
Okay, no.
That I have the right set of letters, but it's NVIDIA's deep learning accelerator. It's a free and open architecture that promotes standard ways to design deep learning inference accelerators. So in essence, we open sourced a way to build these like ASICs essentially for inference. We're also in the process of acquiring ARM. It's always tricky. I believe the regulators are going to approve it. I'm basically just mimicking what I see in our official statements at this point. I have no information outside of what I read myself
Fair.
on that. But we are trying to acquire ARM, and I think we all believe it'll happen. I think the inference world is very interesting. Yeah, you're right. There's just a proliferation of things out there. In fact, NVIDIA's even open source things to make it even easier for people to build more inference. I think that the more inference and the more complex models get, that means that people are going to do more training, which is great. So the more training, more GPUs they'll use for training because it's the best training and processing platform. And so I'm not really sure how the inference landscape will play out, but it kind of all leads back to us, I believe, I hope.
Sounds good. Let's hope we can mass produce enough GPUs, because it seems like no one can ever have enough GPUs on campus here. We have a 100 GPU cluster and it's always overutilized. So last question. Yeah, so last question regarding cuDF and BlazingSQL, that the benchmarks that you're showing are pretty impressive. Is there a software play from Nvidia to take on the analytical database market then in the future? Like, why would someone need to use columnar database systems or data warehouse systems or even things like Spark and Databricks if they can get a cheaper total cost of ownership in the cloud using tools like these? What's your speculation on that? Is Nvidia going to become a software company too in the database world?
Nvidia is a software company.
In the database world?
Yeah, I mean, I think we're a data center software company. We were a game company, then hardware, then supercomputing. Now we're a software company. And one of the reasons why we open source Rapids, there's about 500, like, I think some, analysts, they produce this like page of a bunch of logos, and they put boxes around the logos, and they say what they all do. There's like 500 companies that are all viable and, making a lot of money. There's no way Nvidia is going to compete with 500 companies. But if we put out software that is better, faster, cheaper, hopefully all 500 of those companies will eventually rewrite their software to run on top of Nvidia GPUs. So I think that's one of the core things about Rapids, cuDNN. Nvidia doesn't have a deep learning framework. We have cuDNN. cuDNN accelerates all the best deep learning frameworks. I'm sure you could find a deep learning framework that doesn't use cuDNN. I will also show you a deep learning framework that's probably not that efficient. And so the goal is always the same for us to build really great core libraries. And when we talk about building bridges, we're very serious about that. We want all these other analytical packages to use Rapids core libraries as well. And so we have a team working on accelerating Spark. Today, Dask and BlazingSQL and the Python side is significantly better. Maybe in the future, people will just start using Python more than Java, or maybe the Java ecosystem will provide better NVIDIA integration. We work very closely with a lot of database vendors, and I always, I don't like to name names, but you can look at our GTC talks and what certain database vendors are doing and GPU integration. And as I said, we talked at ELDB, and I think we really caught a lot of attention. We'd be like, wow, GPUs are really good for just core database things. And so I strongly see a future where GPUs are going to be ubiquitous in data science and data analytics. Maybe not in like NoSQL or transactional databases, just because of it's very serial in nature and very small amounts of data getting added and removed from random things. But when we talk about analytical systems, machine learning pipelines, big OLAP databases, yeah, I truly believe they should all be GPU accelerated. Not just because I work for NVIDIA, but just because so far we haven't. We have found one that can really beat us on any kind of benchmark where we actually have the functionality. And if we don't have the functionality, we'll build it eventually. So.
Okay, sounds good. Thanks, Joshua. So I think we are out of time. Any last question? One last question from the audience? If not, let's give Joshua and Bradley and Heath also another round of applause for visiting us. And thank you for the talk, Joshua, and thank you for answering all the questions.
No worries. And again, please apply for internships. Thanks, everyone.
Great. Sounds good. Take care, everyone. Bye. Stay safe.